I wasn't planning to go down that rabbit hole, but since you brought it up, can you convince me of the utility of the clocks absent the type of data that would actually demonstrate longitudinally their benefit, which to my knowledge, we really don't have yet?
Yeah. So I would say a couple things on that. I think we need to be precise in what we mean when we talk about the clocks, because there's lots of flavors of clocks,
Absolutely,
right?
yeah.
Most people these days, if you just say aging clock, what they really mean are the epigenetic clocks that are showing, the characteristic changes in the epigenome, the epigenetic marks that are seen with age. Again, in every organism where it's really been studied, you do see these characteristic changes in the epigenome with age. And so I would say one place where their utility is clear, at least to me, is as a chronological measure, right? Mm-hmm. Now you might ask, okay, why would I ever want to, use an epigenetic clock to tell my chronological age? I know how old I am, right? But forensics, for example, might be a place where that's useful. Their crime has been committed. They want to know with some level of precision how old the perpetrator is. You could use an epigenetic clock for that reason. And in my world, as part of the dog aging project, there are many dogs, that are rescued. An owner might want to know their age. So I think that is a mm-hmm. real use, and clearly the clocks will work for that. I think really what you're asking though is, can I convince you that the epigenetic clocks and potentially other types of clocks are actually measuring biological aging?
Correct.
Right? And in my mind, that's a harder thing to prove. And personally, I have no interest in convincing you of that because I'm not convinced, right? So I think this is an area where the field is in flux a little bit. And there are certainly scientists who I respect a lot in the field who believe, at their core that these epigenetic clocks tell us about biological aging or can be used to tell us about biological aging. And then there are people like me who want to see the proof. And I think the proof is really being able to show at an individual level, that could be in a mouse, could be in a person, yep. could be in a dog. At an individual level, you can predict someone's biological age at some point in their life, and with some level of precision, predict what's going to happen in the future. What are their future health outcomes? How long are they going to live? Nobody has done that yet. What they've done comes close, I guess. So what has been done is to look at longitudinal studies in people where we have samples from people 10, 20, 30 years ago, measure the epigenetic profiles of those people 10, 20, 30 years ago, and ask how well does that correlate with mortality outcomes, for example, in the future. And they do work to some extent. I think people will debate how well they work. Are they any better than other markers you could look at in predicting mortality? I think that's unclear, but there is some correlation there. So, again, I think it really depends to some extent maybe on how skeptical you are. I'm a skeptic by nature, and I want to actually see the proof. I guess the last thing I would say about this, I'm talking mostly about the epigenetic clocks. Maybe it's worth talking about other types of clocks that people can make. The other thing I want to caution people on, though, is assuming that the epigenetic clocks are the only important thing about aging. There is, again, a small number of very vocal and popular people in the field who talk as if changing the epigenome is going to change everything about aging. We have no data to support that. I just have to say it. That is not true at this point. We have no data to support it. What we know about the biology of aging is that epigenetic changes are one of, depending on how you categorize things, 8 or 9 or 10 molecular processes that seem to contribute, that the field has reached consensus on. It's only one of those things. Is it possible that it is sort of in a hierarchy the most important and drives a lot of those other changes? Yes, that's possible. We don't have any data to support it. So this idea that reversing the epigenome is reversing aging is at best an exaggeration, at worst an outright lie. I mean, it's just not true.
How could that be? What a set of experiments technology-wise would you need to be able to do to even test that hypothesis, say, in a mouse, right?
We're close. Yeah. Well, maybe close. I guess I should qualify that a little bit. Conceptually, we're close. So there have been these factors called the Yamanaka factors that can reprogram the epigenome. So this has been done in cells. Mm-hmm. So if you take cells in culture in a laboratory and you passage them many, many times, you can see changes in the epigenome, just like you might see changes in the epigenome in an animal, in tissues. And you can put these reprogramming factors into the cells and turn them on.
Now, there are 4 Yamanaka factors?
There are 4 Yamanaka factors, but people are trying different cocktails, adding some other stuff in, taking some stuff out. But yes, there are the 4 classic Yamanaka factors. And what those factors do is they basically wipe clean the epigenetic changes that have happened over time. And also what's amazing is that they restore those cells back to if you take it far enough, back to a pluripotent state. So essentially you get, virgin new cells that could differentiate into any cell type in the body, right? So this has been known for many years. What is relatively more recent over the last, 8 or 9 years are people are trying to express these reprogramming factors in an animal. So instead of doing it in cells in the laboratory, do it in an animal. And I think the most compelling work is work in a premature aging model of mice. So it's called a progeroid model, where they're very short-lived, they're very sick, but these reprogramming factors can, extend lifespan by, I don't remember what the exact numbers are, but a significant amount, maybe 40, 50%,
wow. Which
seems like a lot, except you have to recognize these mice live, maybe 25% of the length of a normal mouse, right? Yeah. So they're very sick. So, but there are impressive changes that happen that are consistent with the idea that you fixed or made something better. Okay. So the experiment to do would be to express these reprogramming factors in an old mouse and make that mouse young again. Okay. And this is where I think the exaggeration, I'll use the nice word, has gotten ahead of the actual data. So what has been done is showing that in 1 or 2, maybe 3 tissues, you can see an improvement in function. The most impressive, I think, is work from David Sinclair's lab, where they use this optic degeneration model. Yep. So degeneration of the eye showed that they could reverse that with these reprogramming factors, and then tried to do the same thing in an old mouse. And there was at least, the data was mixed, but I think pretty compelling that you could, to some extent, regenerate the optic nerve in an old mouse. Okay, so that's certainly impressive, I think, exciting, but nobody has ever taken an old mouse and turned it into a young mouse. And when people start talking about reversing aging, right, that implies that you have taken an old animal or person and to some extent biologically made them young again. That hasn't happened. So what I would say needs to happen to really convince me, there are 2 things. So I would be convinced that this is useful, potentially therapeutically, and important. I'm actually already convinced it could be useful therapeutically. But I would become really excited if somebody could do as good as rapamycin in a mouse. So I'm not asking for much, in my view, right? We know rapamycin can extend lifespan 25% at least. Again, our dose hasn't been optimized, but 25%, let's stick with that. And you can reverse functional declines in many tissues, right? So show me you can do that with reprogramming, and I'll be excited. Nobody's done even that yet.
Yeah.
Show me you can take a 2.5-year-old mouse, make it look like a 1-year-old mouse, and then it lives to be 5 years old. I'll be really excited. Look, I'll be all on board. I might even come on your show and apologize for saying that people were exaggerating, although they are exaggerating now. But I think the enthusiasm has just gotten so far ahead of where the science is.
So let's go back to kind of maybe help folks understand what the Yamanaka factors are doing and how one can be sure that even if you fix the aging problem, you don't create a new problem. So if the objective is, I want to take the DNA as I had it when I was young, right? So when I was 20, this is what my DNA looked like.
Yep.
Now that I'm 50, it looks different. It has literally these methyl groups that are sitting directly on the cysteine, residues. Like it's literally on my DNA.
Yeah.
Okay. We want to take those off. Maybe?
Well, so first of all, it's important to understand why that's even a problem, right? Why people think that's a problem, right?
Why is my 50-year-old crappy DNA not as good as my 20-year-old DNA?
So again, this is, taking a step back to sort of basic basic biology, right? So the DNA, right, is where all the information is. But then that DNA has to get turned into RNA. That's called transcription or gene expression. We'll just call it gene expression. And then that RNA has to get turned into protein. And in general, it's the protein that does the work, right? So what these epigenetic changes, the methyl groups that you were talking about, do primarily, we think, is affect expression of the genes. So basically what you're seeing with aging, we think, is a shift in the epigenome that leads to certain genes being expressed that shouldn't be, and certain genes not being expressed that should be. And I think there's a little bit of a debate about which is more important right now, but it probably doesn't really matter.